And so, what are the boundary conditions? At the surface, we say that the vertical displacement delta z corresponds to a traveling wave. So delta z is a times cosine kx minus omega t. We say that a is the amplitude at the surface, all right? The vertical amplitude at the surface, all right? So az of z equals 0 is a, all right? Now, at z equals 0, that means that at z equals 0, az equals alpha plus beta equals a. But z equals 0, remember the solution here. If you put z equals 0 here, you just get alpha plus beta. All right, so at the surface it's very simple. The amplitude A is alpha plus beta. Right? There's one linear equation for the coefficients. Right? The second one is at the bottom. Right? At the bottom, we don't have a delta z because I'm assuming the bottom is flat, and you can't have flow across the bottom. You know, the water can't just bury itself in the sand, and it can't emerge from the sand either. The bottom is flat. There's no vertical velocity. There is no vertical displacement. Okay? So we say dz at minus h, whereas if z equals minus h at the bottom, then dz equals 0. So we put the bottom at z equals minus h. All right? So that's our other boundary condition, alpha e to the minus kh plus beta e to the kh is equal to 0. All right? Now, we can then eliminate one of these two, alpha, beta. All right? We have two equations again and two unknowns. We can find alpha and beta. So we're just substituting for beta from this equation. All right? So we say that az is equal to alpha plus beta, which is equal to alpha plus, well, if you find beta from this equation, it's that. And then we can simplify that, so it's alpha into this thing here, okay? You can also eliminate alpha, so in the same way, you can say az is equal to beta times that thing there, right? And then you can rearrange that, and you can express alpha in terms of the amplitude at the surface, the vertical amplitude at the surface, and these exponentials, and you can express beta in a similar way, right? So we found alpha and beta just by elimination in a pair of linear equations. So now we know everything. We've got the solution, we've got the coefficients, we can write it down, right? And we have an expression for the amplitude. Az equals alpha e to the kx plus beta e to the minus kx. Substitute in these expressions for the coefficients. It gets a little bit complicated. You can simplify it, and in the end, you can express it as the amplitude, the vertical amplitude, as a function of z, is equal to the surface value of that amplitude times this thing, which is the ratio between a couple of hyperbolic sine functions. All right? So sine hyperbolic of k times h plus z over sine hyperbolic of kh. Now remember, z is negative. All right? So z varies between 0 at the surface and minus h at the bottom. All right? So that's the vertical amplitude we've got. We know how it varies with depth. How about the horizontal amplitude? We have to do that as well. Now that, all we have to do is take our expression for the vertical amplitude, which we've worked out, and substitute it into one of these equations that we had before, the differential equation we had before. And, well, you just have to do a vertical derivative, and there you are. Okay, so in the end, we get two expressions for az and ax. Az, the thing I just showed you, is the surface vertical amplitude times this thing. Ax is the surface vertical amplitude times this thing, all right? So what does that look like? We've actually got the answer. We know how the amplitude of the wave varies with depth. Now we want to know, well, we've got a mathematical expression now. We want to think a bit about what it looks like, all right? So what is the hyperbolic sine function? Hyperbolic sine of something equals sine of x, if you like, is equal to e to the x minus e to the minus x over 2, right? And the hyperbolic cosine is e to the x plus e to the minus x over 2, right? So what's the implications for this thing here? Well, how about the vertical amplitude at the surface? So z equals 0. So this thing just disappears, goes to 1, right? This ratio just goes to 1. So unsurprisingly, the vertical amplitude of the surface is A, which is what we assumed in the first place, right? How about at depth? Okay, so what is this ratio going to look like at depth? Well, that's a constant. H is a constant. So when z becomes very big and negative, this thing disappears, right? So it's going to exponentially decrease with depth, right? Assuming that the depth, the bottom is a long way away, right? Horizontal amplitude. So what does this look like? Cosine, hyperbolic cosine of k times z plus h. At the surface, right, well, it's going to depend on this, isn't it? It's going to depend on the depth, right? Because this thing is not equal to this thing. So that means that the surface, the horizontal amplitude, is not necessarily the same as the vertical amplitude. What if the depth is very big, then these two things will come to the same thing, all right? So then it will be a circle. But for fluids which are finite depth, it's not going to be a circle. It's going to be an ellipse, all right? So there's a clue as to what it's going to look like. And I'll come back to those shapes in a minute. Let's just have a look at the way in which we're circulating again. So at the surface we have this delta z, which is proportional to cos omega t, and delta x proportional to sine omega t. We have this ellipse here, okay? And then let's just think about what it looks like when the wave propagates through, okay? So you have these circles, and in shallow water, it will obviously flatten out, right? That's guaranteed from our boundary condition. So if you have an ellipse at the surface in shallow water, and at the bottom you still have some wave motion, it's going to be horizontal. You can't have any vertical wave motion at the bottom. So that means you'll get an ellipse which is going to flatten out into purely horizontal movement at the bottom. I think I mentioned that last time, didn't I? So and now let's have a look at the filled-in circles here, right? And here, and here. So here's a body of fluid which has been kind of marked out, right? And obviously, nothing can enter this rectangle here or leave it. None of these circles can't swap places because they are the fluid, so they will follow the fluid, all right? So this rectangle will delineate a certain identified mass of fluid which might move around, okay? And as the wave approaches it, it's going to move up. And then it's going to move along with the wave, and then it moves back again, and then it flattens out again, right? So it kind of moves up, to the left, to the right, and then down again. And all the time, as it's doing that, first of all, it's flat. You can see that here. And then it's vertical, but with the same amount of fluid in it. So that conservation of area on this diagram corresponds to a conservation of mass, okay? And so the area in this rectangle will always be the same, and it will just distort its shape as the wave passes. So that's just another expression of non-divergent flow. This is the conservation of mass. Right? Right, now we have talked a little bit about deep and shallow water. So what I want to do now is think about what does that mean, because we've been pretty vague about it up to now. Right? So here's a little puzzle for you. Which of these two is deep water and which one is shallow water? I want to come up with a formal definition or a working definition of what is deep water. What does it mean? All right, who thinks this is Shallow. Who thinks this is deep? Who thinks this is shallow? And who thinks this is deep? I've drawn this deliberately to try and mislead you, and I've succeeded, right? Because let me just put the waves in, right? Now, this has a very long wavelength at the surface, right? And there's an elliptical shaped wave displacement which is big enough to reach to the bottom, and it will feel the presence of the bottom. So it's elliptical here, it flattens out, it becomes horizontal at the bottom. This is a circular wave at the surface. It decays exponentially with depth, as we showed on the blackboard. And it doesn't matter how deep this is. It could be 10 times deeper. It wouldn't make the slightest bit of difference to the wave dynamics, because this wave is already gone by the time you get to the bottom. Even though the bottom's not very far away, this is deep, right? Because from the wave's point of view, we can't feel the bottom. We don't know how far away it is. It's irrelevant, okay? Whereas this, even though the way I've drawn it, this is deeper, okay? Because the wavelength is longer, the wave actually is aware of the presence of the bottom, and its amplitude structure will be influenced by that, all right? So it starts off as an ellipse and it flattens out, right? This is shallow water, this is deep water. So the definition, if you like, of deep water is water which is deep enough for a certain wavelength for the wave not to be influenced by the presence of the bottom. So whether or not it's deep or shallow depends on the wavelength, all right? If the depth is significantly greater than the wavelength, we have deep water. If the depth is about the same order as the wavelength, that's shallow water. And obviously, if it's shallower than that, then it's shallow water. So let's go back and look in a bit more detail of what I tried to do on the blackboard, and I did it in a fairly hand-waving kind of way. The deep water case, right? So the depth of water is much greater than the wavelength. This means that kh is much greater than 1, right? Here are our expressions for the amplitude, az and ax, right? So we're going to analyze these expressions under the condition that kx is much greater than 1. And so the waves are confined to the surface, to near the surface, compared to the depth of the fluid. Z is much less than h, right? Well, the magnitude of z is much less than h, right? So under that approximation, the hyperbolic sign of kh is the negative part will just disappear, and we'll just have e to the kh over 2, right? So sine of k times z plus h is approximately the same as cosine of k times z plus h, which is equal to e to the k times z plus h over 2, right? So that means that these two expressions are the same, right, for deep water. If the sine and the cosine are roughly the same, approximately the same, that means there's no difference between these two expressions. What does that mean? It means the waves are circular. The trajectory of the waves is circular. The amplitudes are equal in x and z, right? The z amplitude, az, equals the x amplitude, ax. That makes a circular partial trajectory, which is what we've drawn here, right? So delta z is this, delta x is this. So the only thing that changes is the propagation part, right? The amplitude part is the same, right? So the amplitude is just a times e to the kz. And so that will be something that decays exponentially over a distance scale of 1 over k, right? So the typical vertical scale with which the amplitude decreases is 1 over that coefficient, is the reciprocal of that coefficient, which is going to be 2 pi, lambda over 2 pi. 1 over k is lambda over 2 pi. So the vertical scale of amplitude reduction is related to the wavelength. It's the wavelength divided by 2 pi. longer the wavelength, the deeper the wave goes, right? That's why if this was longer, the bottom would come into play. But the way this is drawn, you can see there's nothing left. Quite a long time before you arrive at the bottom, there's nothing left. So that means that the position of this bottom is arbitrary. It doesn't matter where it is, because the wave is gone by the time you get there. All right? This is deep water. Let's look at shallow water. So for shallow water, we have the opposite. We have KH is much less than 1. The depth of water is small compared to the wavelength. That's a kind of limit approximation. Right? We have the same expressions here in the corner, the wave amplitudes. We're going to apply this approximation. So in this case, the hyperbolic sine of KH is approximately KH. Right? And the hyperbolic sine of K times Z plus H is approximately just K times Z plus H, but the hyperbolic cosine is approximately equal to 1, where this thing is very small. Right? So, what does that give us? Well, it means that these two things are not the same, right? And specifically what we get is that the vertical amplitude, if you work it out, depends linearly on the depth, right? So A times 1 plus Z over H, what does that give us? Right? Well, at the surface, right, we have Z equals 0. So this part disappears, and we just have A. All right, so the amplitude is A at the surface as we imposed. All right? What about at the bottom, at Z equals minus H? Well, this amplitude, this whole thing is going to disappear. All right? This is going to be minus 1. So this thing disappears. That tells us that the vertical amplitude is going to vary between A and 0. Okay? But it's not varying exponentially. It's varying linearly. Right? So if you plot it, it'll just be a linear graph between A at the top and 0 at the bottom. A linear relationship. Very different to what we had with deep water. Right? Deep water, we had an exponential decay of amplitude, of vertical amplitude. With shallow water, we have a linear decrease because it has to reach 0 by the time it gets to the bottom. It can't hang around. It can't hang around with exponential decay. It's in a hurry to get to 0 by the time it gets to the bottom. So just a linear reduction, straight to 0. Right? Now, how about the horizontal amplitude? Well, we just had this cosine function equal to 1 now. So that means that it is A times 1 over KH. Now that's interesting because that is constant. Right? It's not varying with depth. So there's no variation with depth in the horizontal amplitude. So which means you get an ellipse with this major axis, which stays the same, and the ellipse will then just flatten as you go to the bottom. Right. And what is this horizontal amplitude? It's A. A is the vertical amplitude, remember, times this factor, 1 over KH. Now that, 1 over KH, or KH is smaller than 1. We've already established that, okay, because we're in shallow water, which means that this thing must be much greater than 1, okay, which means that the horizontal amplitude is much bigger than the vertical amplitude, which is why we have this ellipse, this elongated ellipse, and that is perfectly consistent with our experience of waves in shallow water, right? Because in shallow water we know that the wave, the vertical wave amplitude is quite small, right? But it moves sideways a lot. Waves that come into the beach, you know they go sideways a lot more than they go up and down. Right? So that is shallow water. Big horizontal amplitude, which is constant right to the bottom. Vertical amplitude is A at the surface, and it reduces linearly to 0 at the bottom.